This episode is supported by the Great Courses Plus. The laws of physics are the same everywhere in the universe. At least we astrophysicists hope so. After all, it's hard to unravel the complexities of different parts of the universe if we don't know the basic rules. But what if this is wrong? There is a hint of evidence that the fundamental constants that govern our universe may evolve over time, and even from one location to another. The laws of physics are the relationships we observe between space and time and the fields and particles that occupy it. Those relationships are often expressed as equations, but they're also governed by the constants within those equations. For example, the standard model of particle physics is comprised of equations that predict the existence and behavior of the particle building blocks of our universe. But the standard model also depends on a set of constants that cannot be predicted by that model, only measured. Things like the mass of the electron and the relative strengths of the forces of nature. Why the fundamental constants take the values they do is a very deep and unanswered question. The answer lies in a deeper underlying theory, a so-called grand unified theory. But some proposed grand unified theories predict something unsettling. They predict that the fundamental constants may not be constant at all, and instead may vary over time and space. Now, we're not going to get into the nitty-gritty of the theory today, we'll come back to it another time. Instead, we're going to look at the experiments and the evidence, because there's a hint of evidence that at least one fundamental constant is, in fact, varying. To measure changes in a fundamental constant, we first need to choose the right constant. Let's try the speed of light. Its value today is 299,792,458 meters per second in a vacuum. But was it always this value? It's been suggested that a changing speed of light might be an alternative to inflation theory or even to the apparent expansion of the universe. But this may be untestable. For one thing, our definitions of the units used to define the speed of light are arbitrary and themselves depend on that speed. The meter is officially defined as the distance light travels in 299,792,458th of a second. And the second is defined in terms of a particular frequency of light emitted by the cesium-133 atom. If the speed of light changes, the rulers we use to measure that speed change also. The speed of light defines the relationship between space and time, so is it even meaningful to talk about it changing independently to its underlying dimensions? In fact, it may be impossible to interpret changes in any physical constant that has units. The dimensions behind, say, Newton's gravitational constant or the mass of the electron all have arbitrary human definitions. To be confident that we've seen a change in a fundamental constant, we need to study a dimensionless constant, one that has no units, and therefore isn't dependent on our definitions of those units. Perhaps the most promising example is the fine structure constant. It's a dimensionless description of the strength of the electromagnetic force. In the language of quantum field theory, it's the coupling strength between the electromagnetic field and a charged field like the electron field. We use the Greek letter alpha to represent the fine structure constant, and its numerical value is one of the most precisely measured quantities in physics, precise to 1 part in 4 billion. Its approximate value is around 1/137, with no units. It's a dimensionless number. No one knows how alpha ended up with this value, but if you change it by much, our universe would look very different. The first measurement of this fundamental parameter was through its effect on the fine-grained structure of atomic energy levels, which is where the constant gets its name. This effect is also how we'll test whether alpha is changing, so let's look into it. Electron energy levels, or orbitals, in atoms are quantized, meaning only certain levels are allowed. When electrons move between levels, they emit or absorb photons with energies equal to that lost or gained by the electron. We see this effect in the sharp spikes or dips in light at specific wavelengths when we observe the spectrum of a gas. We call these features spectral lines. And if you look at their fine-grained structure, you'll see that some lines are split in two, corresponding to very slightly different energies. This splitting is due to the fact that each atomic energy level can host two electrons, and these electrons have spins pointing in opposite directions. Now, quantum spin gives electrons what we call a magnetic moment. They have magnetic fields, just like a little bar magnet, or electric currents rotating in a ring, even though there's no actual rotation. These same electrons are also orbiting the atomic nucleus, and that motion generates its own magnetic field. The magnetic fields produced by an electron's spin and by its orbital motion actually interact with each other in an effect called spin-orbit coupling. There are two stable configurations for this interaction. The little bar magnet may be aligned with the orbital field or opposite to it. Alignment with the field is the more stable state. It has a slightly lower energy than the opposite alignment. So when electrons jump between orbitals, the energy they absorb or emit depends on their spin alignment. The result is a very small difference in the wavelengths of the spectral lines produced by those transitions. Okay, but what's all of this got to do with the laws of physics changing? Well, the magnitude of this wavelength split depends very strongly on the fine structure constant. To measure changes in alpha, we just need to look for changes in the magnitude of line splitting. The key to this measurement is quasars. Remember quasars? Insanely luminous maelstroms of superheated matter surrounding the most massive black holes in the universe? These things can be seen out to billions of light years. When a quasar's light passes through giant clouds of gas on its way to us, elements in those clouds absorb photons to produce spectral lines. By looking at many quasars, we can find absorbing clouds that existed in different past epochs of the universe. Fine structure splitting in those absorption lines can then be used to track changes in alpha through cosmic time. As it happens, a group of researchers in Australia did exactly this. They used the Keck telescope in Hawaii to study iron and magnesium absorption lines from clouds along the lines of sight of 143 quasars. Their results suggest that alpha was slightly smaller in the past, by around 1 part in 100,000. In their 2004 paper, they claim 5 sigma significance, indicating a confident detection of a change in alpha. This is intriguing, but get this. The researchers then pointed the Very Large Telescope in Chile at a different part of the sky, and they found that alpha varied in the opposite direction. Looking in the new direction, they found that alpha was larger in the past, suggesting both a temporal and a spatial variation. The significance of the spatial variation was claimed to be 4 sigma, so still tentative. Now, this is all highly suggestive, but these results are by no means widely accepted. Some recent attempts to reanalyze the data indicate only a 2 to 3 sigma significance, which is consistent with no change in alpha. The challenge here is that the measurement is really difficult. Photons from these extremely distant quasars and gas clouds are massively redshifted, their wavelengths stretched out due to the expansion of the universe. That redshift needs to be carefully accounted for, and there are many other potential systematic errors that could masquerade as a change in the fine structure constant. These potential pitfalls are why it's so important for scientific experiments to be reproduced by multiple teams before results can be accepted. For now, all of this remains a tantalizing possibility until more and better experiments are performed. Other efforts are underway. For example, there's the Oklo Natural Nuclear Reactor in Gabon in Central Africa. This uranium deposit underwent a natural fission event 2 billion years ago. Scientists are analysing the remaining decay products to see if alpha was smaller when the event took place. We're also trying to develop atomic clocks accurate enough to track changes in alpha in real time. If the fine structure constant is changing, then it's not changing by very much. So why do we care? Well, any measurement of a change in alpha may provide evidence to constrain the grand unified theories that predict such changes. We are currently in dire need of any such evidence, and verification of a change may be a way to solve the fine-tuning problem. certain astrophysical processes that seem to be necessary for the appearance of life are quite sensitive to some fundamental constants, alpha especially. In fact, if alpha was much different, then chemistry would work differently, or not at all. The stars themselves would never have formed. It might seem lucky that alpha is fine-tuned for a universe with the warmth of stars and a rich and complex chemistry, both essential for life. But if the fundamental constants vary from place to place, then it's not surprising that we find ourselves in a part of the universe conducive to stars and to planets and to life. Scientists are also looking into the variation of other dimensionless constants, such as the proton-electron mass ratio and the more obscure proton gyromagnetic ratio. The search continues. Larger surveys with future generations of telescopes, more refined cosmological models, and better atomic clocks will all help scientists shave down those experimental error bars little by little. We may one day find that our sacred laws of physics and their underlying constants aren't so constant after all, beyond our little patch of space-time. Thanks to the Great Courses Plus for sponsoring this episode.